One-sided limits. What are one-sided limits? These are limits of the form limit of f of x as x approaches a from the left. So you should note that this means x approaches a from the left, right? You also get this limit of f of x as x approaches a from the right. Right, so this means x approaches a from the right. Example 1. Refer to the figure and evaluate. Right, so the first one, the limit of f of x as x approaches 1 from the left. So you're approaching 1 from the left, and you can see what's happening to the output. See that the output is approaching 0. Right? Your f of x is approaching 0. So the next one, the limit of f of x as x approaches 1 from the right. So as x is approaching 1 from the right, you can see that the output here is approaching 2. Example 2. Here we're dealing with a split function. All right, the limit of f of x, you can see that the critical value of x is 0. So that's 0 to the left of 0. Right, from 0 and to less than 0. Your defining equation for the function is this. F of x is equal to negative x plus 1. So evaluate the limit of f of x as x approaches 0 from the left. So this is equal to the limit of negative x plus 1 as x approaches 0 from the left, and you can see that this gives us a value of 1 when you evaluate the limit. Now, the next one, we want the limit of f of x as x approaches 0 from the right. So it means x is greater than 0, right? So when x is greater than 0, in other words, to the right of 0, the defining equation is this: f of x is equal to 2x plus 3. So this is now the limit as x approaches 0 from the right, and you're taking the limit of f of x, that's 2x plus 3 in this case, and you can check when you evaluate the limit, you end up with an answer of 3. As x approaches 0 from the right, your 2x also approaches 0, so you end up with the limit being 3. So example 3, right? Again, for g of x, we got a split function. The crucial value of x is 1 in this case. The change occurs at 1. So let's check what happens. When x is greater than or equal to 1, right? So greater than or equal to 1. So we're dealing with this part. Right. And the defining equation that's going to come into operation is this one. Then we're looking at g of x when x is less than 1, right? For this part, you can see that the defining equation is going to be given by what's over here. So evaluate 3.1. G of x as x approaches 0 from the left. So in other words, x is less than 1. So here you end up with the limit as x approaches 1 from the left. And we do the substitution for g of x. In this case, it's 1 minus the square root of 1 minus x. So as x approaches 1 from the left, you can see that the part under the square root sign is going to approach 0. So we're going to end up with 1 minus 0, which is 1. Right, so 3.2, the limit of g of x as x approaches 1 from the right. So this is the limit as x approaches 1 from the right. So in other words, x in this case is going to be greater than or equal to 1. Right, so looking at the purple arrow above, in this case, your replacement for g of x is 1 sorry, it's x plus twice the square root of x minus 1. So you can see from this now that as x approaches 1 from the right, so x is going to approach 1, plus you're going to get 2 multiplied by, right, the part under the square root sign is going to approach 0, so you'll end up with the square root of 0, which is 0, and this gives us 1, right? Now from example 2, we've got the limit of f of x as x approaches 0 from the left, that gave us 1, and the limit of f of x as x approaches 0 from the right, that gave us an answer of 3. So the limit of f of x as x approaches 0, right? Because the one-sided limits are not equal, so we say this limit does not exist. Right? From example 3, the limit of g of x as x approaches 1 from the right, right? We had an answer of 1, and that was also equal to the limit of g of x as x approaches 1 from the left. Right, so therefore, since the one-sided limits as x approaches 1 are equal, then we conclude that the limit of g of x as x approaches 1, in this case, it's equal to 1. Right? You must study example 1 on page 344. We now look at continuous functions. This is on page 344. Right, we look at this figure. Right, the graph is given in blue. You'll notice at x is equal to a, there's a hole in the graph. At x is equal to b, there's also a hole in the graph. But f of b, you end up with this point, right? The point with those coordinates. You'll look at c. There's like 2 branches to the graph, right? You're coming from the left and to the right, and from the right, you can see that the limits are going to be different. So the graph is disjoint. At D, you've got a vertical asymptote, right? As you approach D from the left, the output approaches positive infinity. as you're going to approach D from the right, the output is going to approach negative infinity. So we now can conclude the following. The graph is not continuous at x is equal to a, x is equal to b, x is equal to c, and x is equal to d. Right? So we now come to the concept continuity of a function at a number. So a function f is continuous at a number x is equal to a if the following conditions are satisfied. Now you look at it, there are three conditions. All three conditions must be satisfied. Right? F evaluated at a is defined. 2, the limit of f of x as x approaches a exists. For that to happen, the one-sided limits must exist. So you need to apply theorem 3 for this part. And then if you look at the third condition, which is a, that's what you got from the second condition, right? So this will have to exist to start off with, and that must equal to f of a, and your f of a really was your first condition, right? Now if we apply this to above, for at a, you can see that the limit of f of x as x approaches a, that exists, right? But the first condition, f of a, does not exist. Right? If you look at b, x is equal to b, your f of b is not equal to the limit of f of x as x approaches b. And if you look at C, your f of C is not equal to the limit of f of x as x approaches C. At x is equal to d, you got a vertical asymptote. Right? You must study example 2. That's on page 346. We now move on to properties of continuous functions. It's on page 347. A constant function f of x is equal to some constant is continuous everywhere, right? To the identity function f of x is equal to x, in other words, the input is the same as the output. This is the line y is equal to x. This is continuous everywhere. And if f and g are continuous at x is equal to a, then the f of x raised to n, where n is a real number, is continuous at x is equal to a whenever it is defined at that number. Right? You know, like the square root of a negative number is undefined, so you need to be careful for those types of cases. Number 4, the sum of f and g, or the difference of f and g, is continuous at x is equal to a. 5, the product of f and g is continuous at x is equal to a. And 6, the quotient of f and g is continuous at x is equal to a, provided g of a is not equal to 0. We know that the denominator can't be 0. So you need to look at that, know the properties of continuous functions. Then continuity of polynomial and rational functions. 1, continuity of polynomial and rational functions. 1, a polynomial function y is equal to p of x is continuous everywhere. So a polynomial function is continuous at every value of x. A rational function, r of x is equal to p of x over q of x, is continuous at every value of x where the denominator is not equal to 0. Right, you must study examples 3 to 5 onwards, from page 347 onwards. Right, and there are now 7 examples which you need to try out. I'm going to stop the lecture over here. You'll find the solution of these on the PDF of the lecture.